Welcome, high school teachers. In this module, we're going to extend Archimedes' law of the lever to some somewhat more general situations. And then we're going to examine the connection with some statistics. In particular, the idea of the expected value of a probability distribution. So it's going to connect to a very important new development in the curriculum here in Australia, where statistics is going to be playing a considerably wider role than it has previously. All right, so let me remind you that we've been talking about levers and balancing, and Archimedes' law of the lever played a prominent role. And we talked about it in the context of a class 1 lever, where the fulcrum was in between the two masses. And so, for example, with this lever here, we have a situation where we have mass of 4 here, a mass of 10 here, and fulcrum here. And there is balancing because of this fundamental equation being satisfied. So the m1 times v1, v1 is the vector from the fulcrum to where that first mass is. That's the vector minus 5. So we multiply this times minus 5, we get the vector minus 20. And if we add to it m2 times v2, we're adding 10 times the vector 2. Well, the total is the vector 0, telling us that we do have balance. And I want to point out that this lovely formula actually also applies to the class 2 and the class 3 levers. But we may have to be a little bit more flexible about what we consider as a mass. In particular, to balance this kind of lever, we will often require an upward force there, represented by this little balloon here. So that's a helium balloon, which is pulling upwards. So let's have a look at this one here. We have a fulcrum here, a mass of 4 at this position here, which is 3 along. And then over here, at position 8, there is this balloon. Well, we can represent this balloon momentarily, or its force, by m2. And then the balance equation would be balance occurs when the first mass of 4 times the first vector of 3 plus the second mass of m2 times the second vector, which is 8, adds up to the 0 vector. Well, that occurs precisely when m2 equals minus 12 over 8, or minus 3 over 2. So the conclusion is that if you want to lift up that mass of 4, which is sort of like in your wheelbarrow, you have to exert an upward force corresponding to a mass of 3 over 2, but in the upwards direction. Here's a class 3 lever where the force is between the fulcrum and the mass, also represented by this little red helium balloon here. And then the equation of Archimedes is that this unknown mass m1 here times the vector 5 plus the mass m2, which we're assuming is 4, times this vector here, which is 7 in this case. That should be equal to 0 for balance. And that happens when m1 equals minus 28 over 5. So almost minus 6. Showing, I guess, also that if we want to lift this mass of 4, it's more efficient to use this kind of class 2 lever, where we only have to apply an upward force of 3/2, rather than this class 3 lever, where we have to apply considerably more force at this point here. Correspondingly, if we want to do something that's rather delicate and we want to have a very fine control over things, then we're probably better off using this kind of situation where if we have too much strength, the strength is sort of diminished by the lever. All right, so we see that Archimedes' law of the lever applies to all 3 classes of levers. Archimedes' formula is really a great formula because it extends in a lot of other different directions. In particular, it works when we have more than two masses. For example, suppose we have a teeter-totter or seesaw with, say, 3 kids on it. Those 3 kids can still balance themselves if they organize their positions in the right way. So here we have mass of 5, a mass of 2, a mass of 8, and we claim that there is still balance going on. We can check it by using Archimedes' law. For that, we need to understand what are the 3 vectors from the fulcrum to the 3 masses. So we're going to call this mass m1, and we could call this vector v1. And if this is mass m2, then this would be the vector v2. And this is the mass m3, and this would be the vector v3. So the balance equation occurs because if we look at m1 times v1 plus m2 times v2 plus m3 times v3, the total moment is m1 is 5, v1 is 1, 2, 3, 4, negative 4 because it's in the left direction, plus m2 is 2 times negative 2, and m3 is 8 times the vector 1, 2, 3. For a total of minus 20, minus 4, plus 24, or 0. Total moment is 0, so we have balance. All right, so let's have a look at this problem. We have a situation where we have 3 masses. 2 of them are regular ones, mass of 7 here, a mass of 5 here. And here we have a negative mass or an upward force at the position 2. And we're interested in finding out where is the center of mass. Where can we put a fulcrum so that this somewhat fancy lever still balances? Well, let's let this unknown center of mass be some coordinate, let's say C. Right? So C is going to be this unknown center of mass that we're trying to find. Then the balance equation of Archimedes is m1 times v1 plus m2 times v2 plus m3 times v3 ought to equal 0. And m1, m2, and m3 are these 3 masses. That's 7, that's minus 10, and that's 5. And v1 and v2 and v3 are the 3 vectors emanating from the center of mass to the positions of those 3 masses. So for example, v1 would be this vector here. v2 would be this vector, and v3 would be this vector. Of course, those vectors are going to involve this unknown coordinate C. So let's see if we can write this down involving this unknown coordinate C. m1 is 7. v1 is the vector from C to 0. So it's the vector 0 minus C. m2 is minus 10. And the vector v2 is the vector from C to 2. So it's final minus initial. That's how you find the vector from the endpoints. And finally, m3 is 5. We have to multiply that by the third vector v3 from C to 6. That's going to be 6 minus C. So all of that should equal the 0 vector. Okay, so that's a linear equation in C. And hopefully we can solve it pretty easily. Let's have a look. So the constant terms, 7 times 0, and then plus minus 10 times 2, plus 5 times 6. And if I bring all the C terms over the other side, I'll have C times 7 minus 10 plus 5. So there's a coefficient of C here, coefficient of C here, coefficient of C here. I'm bringing that all to the right-hand side. You see, in fact, we're just getting the sum of the masses there. And what's the answer then? 0 minus 20 plus 30 is 10. So 10 equals c times 2. So 10 equals c times 2, which tells us that c equals 5. So our center of mass is actually right here. That's the place where the lever balances. So it turns out that centers of mass are closely connected with the notion of expected value or mean from statistics. And statistics is going to be an aspect of mathematics that's going to be playing a much bigger role in the new Australian curriculum. So to make this connection, let's have a look at a pretty familiar situation to all of you, the idea of average of a bunch of test marks. So suppose we have a teacher who gives a small class, say 8 students, a test, and that here are the 8 marks. There's a 4, a 5, 6, 6, 6, 7, 9, and 9. Well, we can represent those marks on a kind of frequency graph. Here are the various possible marks, and these little bars represent how many students got that particular mark. This is looking a lot like a mass distribution that we've been talking about. We can think of these blocks here as actual masses. Okay, now let's compute the average of this set of marks. So average, maybe we'll write mu for average. How do we calculate that? Well, the standard formula is that we just take the marks and we add them all up. 4 plus 5 plus 6 plus 6 plus 6 plus 7 plus 9 plus 9. And then we divide by 8. All right, so you can check that this sum is actually 52. So our sum is 52 over 8, which is 6 and 4/8, or 6.5. That's the average. And it turns out that this average is also exactly the same as the center of mass of this probability distribution. Or to put it another way, it's the place where we'd have to put the fulcrum so that those masses balance. That we actually get a lever that's balancing here. Okay, so there's the value 6.5, what we're calling mu. Now I want to rewrite this in a suggestive way, so let's have a look at this formula and just rewrite it a little bit in the following way. I'll take the 1/8 out front, and then I'll write it as 1 times 4 plus 1 times 5 plus 3 times 6 plus 1 times 7 plus 2 times 9. So here what we're doing is we're giving an alternate way of calculating the average, where you don't add up all the 6s, you just count how many 6s there are and multiply the 6 by that number or that frequency. And this also, I guess, makes it clear why this average connects with the center of mass, because this is the same kind of formula that we've been seeing that we get when we calculate the center of mass. And a great exercise for you is to actually calculate the center of mass of this thing and see that you're going to get exactly this kind of expression. But now I want to go a little bit further. I want to introduce a probabilistic aspect to this situation. At this point here, it's completely deterministic. The class has done this test, and these are the marks they've gotten. But it turns out that we can look at this situation from a probabilistic point of view. We can introduce a game. All right, let's play a little monetary game, you and I. So this is a game that's created from these marks that we've been talking about. So we have these 8 marks ranging from 4 to 9. These are marks that some class of students got on their math test. We're going to take this very deterministic thing and make a game out of it with an element of chance. And the way we're going to do that is I'm going to take 8 cards and put these numbers on them. So there are as many cards as there are numbers there. All right? And the game is that you get to pick one of these at random, and I'm going to pay you that many dollars. This is just a theoretical game. It's not really going to happen. All right, so let me shuffle these cards. Okay, and you're going to have to choose well. Okay, so good luck. So choose one of those cards for me, all right? Here they are, so you can choose one of them. Which one would you like? Maybe that one there? That one there, you say. All right, fine. That one? Okay, good choice. What is it? 9. You've done very well. I'm going to pay you $9. All right, let's play it again. We'll put that 9 back in the deck. Shuffle again. And you're going to choose one more time. Which one would you like? That one? Maybe this one. Okay. It's a 7. Not too bad. So you've just won yourself another $7. And let's play one more time. Put that back in. Shuffle again. Completely random. No one knows what's going to happen. Okay, and now you get to choose another card, and your choice this time is maybe the one behind here. All right, excellent. And that's a 6. So from this deterministic situation, we've cooked up this game. And one interesting question that I would like to ask is, how much is this game worth? So how much should I charge you so that on the long run, I'm going to break even? So the question is, how much is this game worth? And in statistics, we say that in slightly different language. We ask, what is the expected value? The expected value of the game. Well, the situation is now very similar to what we had on our previous slide. The various possible outcomes are 4, 5, 6, 7, 8, 9, 10. These are dollar outcomes. And now these boxes above these numbers represent the probabilities of getting these various outcomes. And the probability of getting a 4, if we play once, is 1/8, because there's 1 out of 8 chance to get a 4. The probability of 5 is 1/8. The probability of 6 is 3/8. 7 is 1/8. 9 is 2/8. And altogether, these probabilities sum up to 1, as they must. So this is very much like the frequency diagram that we had, but it's more a probability diagram. And because we've just scaled essentially these masses down, we can still interpret the situation as being a bunch of masses on a line, but now the meanings of the masses are they're representing probabilities, whereas before they were representing frequencies or perhaps proportions. So where is the expected value? Well, you won't be too surprised, I'm sure, to find out that it's 6.5. That is the expected value. It's the same as the average of the class marks. It's the same as the center of mass of the previous mass distribution of frequencies that we talked about. And it's, in this case, the center. And for us, it's the expected value. Or another word for this is mean. And what's the formula for it? Well, I'm going to write that over here. I'm going to rewrite the formula that we had on the previous page, now in terms of probabilities. Okay? So it's mu is 1/8 times 4 plus 1/8 times 5. And we keep on going all the way up to 2/8 times 9. That's just another way of rewriting what we've already had. And we're going to get exactly the same number that we got before, which was 6.5. But what we see is a very important formula here, that to get the expected value or mean, we're multiplying probabilities times values and summing up those products of probabilities times values. Let's have a look at another game where we can calculate a similar expected value or mean. Okay, let's take our understanding of expected values of games and apply it to perhaps a hen's party or a buck's night. You've got some friends over, you want to play a little bit of some games, and you want to make a little bit of money on the side. So here's a game that you might play. The game is that you roll 2 dice, and I pay you the total shown. For example, if you roll 2 dice and 2 6s are shown, then that's the best possible outcome. I'm going to pay you $12. If you roll 2 1s, I'm going to pay you only $2. So your outcome per game is somewhere between $2 and $12. And we're kind of interested in how much is this game worth? In mathematical terms, what is its expected value? Well, we'll look at it from the same point of view as we did the last example. There are the various outcomes, all the possibilities from 2 to 12. And each of those outcomes is associated with a probability. There's a certain probability of getting a 2, a certain probability of getting a 3, and so on. The probability of getting a 2 or a 12 is 1 over 36. Because there's only one way of getting a 12. You have to land with a 6 and a 6. So it's 1/6 times 1/6 equals 1/36. Calculating these other probabilities is not too hard, and it's somewhat interesting that they sort of march up linearly. 1/36, 2/36, 3/36, up to the maximum of 6/36, or 1/6 for rolling a 7. So 7 is the most likely outcome if you roll 2 dice. These probabilities, by the way, are quite important for people who play backgammon or other dice games. Okay, how are we going to calculate the expected value? Well, this formula that we saw last time is we're going to multiply probabilities times values, and then we're going to sum them all up. It's essentially the same formula that we're using to find the center of mass of a mass distribution. So what do we actually get in this situation? Well, the probability of 1/36 times the value of 2, plus the probability 2 over 36 times the value of 3. And you have to keep going, multiplying probabilities times values, and then adding them all up until the very last one is 1/36 times 12. And you can do that calculation. Maybe it helps if you take the common denominator of 36 out. It's easier to work it out. And it turns out to be exactly 7. So the expected value is exactly 7. Geometrically, we can think about this the way Archimedes would have. He would have said, well, what we really have is a bunch of masses on a lever. The places where the masses are the various values. And the masses are really the probabilities, representing how likely it is to get these various values. So we get this distribution, which peaks at 1/6 over 7, and then it goes down. And what we've just calculated is the fact that this whole thing will balance at the center of mass, or the expected value of 7. And when you look at it geometrically like this, it's pretty easy to see that that's going to be the case, because the whole thing is symmetrical, and clearly 7 is sort of the center of things. It's obviously going to be the place where things balance. So that's how much the game is worth. The game is worth $7. If you have to pay $7 to play this game, and you play it over a long period of time, well, sometimes you'll get 12s and 9s and 10s, and you'll be ahead of the game. Sometimes you'll get 2s, 3s, and 4s, and you'll be behind the game. But on average, you will break even. So, since we're organizing the hen party, let's charge everybody $8 to play. We'll make a little bit of profit on the average. So on the average, if we charge $8 to play, people can expect to lose $1 per game. But it depends very much on the particular luck sequence that they have, if that actually happens or not. So we see that centers of mass, Archimedes' formula, is also very relevant to teaching students about probabilities and about expected values or means of probability distributions. It connects naturally also to averages and discussions of proportions. In our next module, we're going to have a look at two-dimensional variants of things. We're going to look at vectors in the plane, barycentric coordinates, and calculate where things like quadrilaterals and triangles balance.